All right, so notes 4 is confidence intervals for a difference in means. Okay, so just like with proportions, we started with like a one sample proportion test, and then now we're moving on to or one sample proportion like interval kind of thing to like a difference in two samples, and now we're doing the same thing for means. Okay, so for the sampling distribution for difference in means, of course, we always have to worry about the conditions, and I'm sorry, like you're gonna have to write this out for this one, but it is a little bit different when we have two samples going on. I want to make sure that you like write it down one more time. All right, so. Our shape, of course, has to be approximately normal, okay? And as long as our two sample sizes are greater than 30, we can use the central limit theorem. Okay. Or if one or both are less than 30, then each population should be normal. Okay, and if we don't know either of these two things, remember we will need to, or let me just give you a look at if not. So if not, if it fails both of these, then we graph. Okay, and then check for strong skewness or outliers. Okay, next up is our center. Okay, and we're dealing with our mu. So mu of x1 would be equal to the mu of 1, and the mu of x bar 2 will be equal to the mu of 2, and we want to combine those. It's pretty quick. It's mu x1 minus x2 is going to be equal to mu 1 minus mu 2. Okay. All right. As long as both samples must either, we know this, got to be randomly selected or randomly assigned. Okay. And then spread is the most complicated looking one. Okay, remember we're looking at standard deviations will be equal to standard deviation 1 over the square root of n. And then we'll also have our standard deviation 4x2, which would be standard deviation of 2 over, this should be n1, sorry, and then n2. Okay. All right, and then remember when we want to combine spreads, of course, we're going to want to combine the variances, which we get by just taking both standard deviations and squaring them. Okay, so for that, okay, x1 minus x2. Okay, we're going to get this big formula. We're going to square the first standard deviation. We're going to add it to the square of the second standard deviation. And then we're going to clean it up a little bit because this square is going to come inside here and do a little bit of work. So ultimately, our combined standard deviation looks something like this. We will have standard deviation 1 over n1, or squared, sorry, and then plus standard deviation 2 squared divided by n2. Okay. And then as long as, this will work out as long as our we satisfy the 10% condition. Remember, we have to check both n1 to be less than 10% of population of n1, and then n2 is less than 10% of the population of n2. Okay. And then also remember, if we're running an experiment, there's no need to check this. So if we're doing some matched pair design stuff from the last lesson, we would not have to worry about this. Okay. And then, of course, we know we're not dealing, we will rarely know the population standard deviation, so we'll have to use the standard deviation instead. Okay. So for this, remember, it's just going to replace all of those standard deviations with our sample standard deviation, sorry. So it just changes to look like this. Okay, not much of a difference. All right, so now we know, since we're dealing with this whole t distribution thing, we know there's the degrees of freedom, and what do we do when we have two samples for degrees of freedom? Okay, well, we have two options. Here's the first option, okay? So and before you start to panic, and I'm really sorry I'm not there to see the panic go across the classroom, you will never ever have to use this one. It's just, I want you to know, like, if you use your calculator to find your degrees of freedom, this is the formula it's using. Okay, and this will rarely give you a degree of freedom as a whole number, but you are allowed to use this, but I would never recommend to actually calculate this by hand. Okay, there is, if you're as typo prone as I am 100% going to make a mistake trying to use that formula, okay? But this is what your calculator is using, okay? All right, so let's look at the method we're going to use, okay? And the one that's much, much easier to do by hand, okay? So option 2, the degrees of freedom is just going to be the smaller of N1 minus 1 and N2 minus 1. Sorry, not 2, minus 1. So we look at the degrees of freedom from both samples, and we will take the smaller of the two. Okay, so we consider this a conservative method because if when you're using this, the confidence interval will have a margin of error as large or larger. Okay, all right, so our confidence interval will be as large or larger than what is needed. Okay, or than, sorry, they should also add than. Okay, and then the significance test will give a p-value that is equal or greater than the true p-value. Okay, so it is a little bit of there is a little bit of an error involved, but we understand that when we're running through this degrees of freedom method than the other. Okay, so this is what you want to remember. This is what you want to memorize. Don't worry about that. Okay. All right, so we know how to check the conditions. We've done that 1,000 times. So just there, it's there for your like a summary. Okay. And then when the conditions are met, we're going to have this formula. Okay, so it's going to look somewhat familiar. We're going to have x bar 1 minus x bar 2 plus minus our t star times the s1 squared over n1 plus s2 squared over n2. Okay. All right, and then we know that the t star is going to be the critical value with that c percent of its area between negative t and positive t for the t distribution with degrees of freedom using our two methods of degrees of freedom. So again, we've got our conservative method, and then we can run the test on the calculator to see the calculator version. Okay, that's going to be the end of this video. The next video is going to be an example.